Hello everyone, welcome to my channel. In this session we will try to crack data pages in SQL Server. This is the first session of SQL Server page internal series concentrating on data pages. In the next sessions we focus on index, text image, PFS, IAM pages. Okay, so furthermore, based on our acquired knowledge, we will try to resolve corruption issues in SQL Server more professionally. In this session, first, I will briefly show how SQL Server utilizes pages for reading and writing operations. Then I will share internals of pages at very high level. Then I will crack data pages very much internally so that you will be able to understand how data pages are built in SQL Server. Okay, let's get started. Firstly, let's try to see high-level flow of select query in SQL Server. When user makes query, the request is first checked in CMD parser, then execution plan is generated in optimizer for this query. Then, based on this execution plan, query executor brings required data from storage. For this, it uses access methods which uses buffer manager to request required data. Very much straightforward, right? Buffer manager is one of the most important components in SQL Server. What does it do is, it will go to buffer pool in memory and tries to find pages there which contains required rows that client is requesting. If the page does not exist in buffer manager, in buffer pool, it will bring the page from hard disk to buffer pool and locates the rows. After rows are found, they are returned to the client. So, in this session, we will dive into this very much important part in SQL Server, pages. So, why you should know pages? Let me tell you a few important reasons. Firstly, knowing the structure of pages helps you diagnose and resolve performance issues. For example, when you face high fragmentation or slow performance because of inefficient indexing, you can grasp the issue much more easily and troubleshoot. Okay? Secondly, understanding how data is stored and how pages are built internally helps you understand data corruption issues and troubleshoot. Many engineers just when they find the data corruption issues, they just run DBCC command, right, and tries to resolve it. But first of all, they should understand what is corruption, how does it occur, right? In what form it occurs. It's very much important. To understand that, you should know how pages are built, okay? And also, understanding how data is stored and accessed on pages helps you optimizing query performance. For example, in many cases, the slowness comes when page reads and writes increases, right? So, in that case, how we can decrease page reads and writes to improve performance? For this, you should know what is page, right? How they are formed, how they are internally created. That's why you should understand pages. So, let's quickly learn how data pages are built first. Each page begins with 96-byte header that's used to store system information about the page. This information includes page number, page type, the amount of free space on the page, or object ID, for example, right? Right after page header, data rows are stored. Then, if data page is not full, free space does also exist from this 8 kilobyte space. Then there is row offsets. Row offsets are region of the page which tell you where each row starts and ends within the page space. Okay, this is very high level architecture, right? Let's now crack data page with a real example and see this architecture in action in very low level. Firstly, I create table called test. Then I insert 7 rows to this table. These rows fit in one page because they are less than 8 kilobyte. Then by using DBCC IND, I find page ID. Here, page type equal to 1 means that this is a data page ID. By using this page ID, I dump the page. This command firstly provides buffer information. SQL Server uses this information to track the page in the buffer. Our page starts from here. Firstly comes 96-byte page header showing information about the page. I point out important information here only, okay? Here, page ID first. This means page ID 512 is located in file 1. Then M type equal to 1. This means that this is a data page. You can refer to this table for other page types. Then M level equal to 0. This is a level that the page is part of the B tree, okay? Where it is located, it shows. If the page is located as a root level, this becomes 0. For index pages, you can see different numbers here depending on the level of the index tree where page is located. For non-index page, this is always 0. Then you can see object ID, which is table ID here. Then you can see other information which helps SQL Server to track this page. After this information, here comes data, okay, in hex format. One important point, this header is also included in this data part. DBCC command is just extracting information from here and representing to us to make it more readable. This is our page with header at the beginning. Then inserted rows and free space. At the end, you can see row offset information. Let's crack this, okay, this information. For this, I copy this to OneNote to make the presentation easier. First, you can see hex numbers with 1 and 2 numbers, okay, hex numbers. These are all free space in the page. Let's color this. After coloring, I delete some part of this for presentation purposes only, as this part anyway is free space and the same, okay? Okay, then at the end, you can see row offsets. This offset table has been provided by DBCC command to help read the page information. At the beginning, until here free space, there is header and all the rows we inserted. Let's color this with another color. Some parts of this data is readable from here, like Bob and Julie, right? Let's try to understand this page. Here, every 2 characters represent 1 byte. Here, there are 4 bytes, 4 bytes, 4 bytes. Overall, in first line, there are 20 bytes. So then next line also 20, then 20, until here, overall 80 bytes. Then 84, 88, 92, and 96 bytes. As you might remember, page header consists of 86 bytes. So all the data until here is page header. I mean this page header information in hex format. I color this with another color to make it different from below data. Right after header, here comes first row we inserted, okay? SQL Server knows this position from row offset below, okay? Where this first row is starting, SQL Server knows it from row offset. Row offsets are recorded in reverse order here in the end of the page. This is the first row, starting position. There is one tricky point here. We should swap the position of 2 bytes here. Then hex of 60 becomes equal to 96, right? This means first row is starting after 96th byte here. The same information is given in the offset table below. Bingo, right? We are now starting to understand what is offset table. So where does second row starts? For this, we do the same thing. Oh, sorry, this should be 77. Hex of 77 becomes 119. The same comes from offset table here, right? Offset table is already showing this to us. Let's color first row with another color here, 100, 104, 108, and until here 119th, right? It is the starting position of second row, so therefore we just stop here. This is the first row. The second row is starting from here. Let's color this. So we follow the same for other rows. Row offset is providing information of starting and ending position of each row in the page. So last one here is E8, hex E8, which means last row is starting from 232nd byte till the free page space starts. Okay, so this is the whole page structure we talked about, 7 rows. If we put all this information back to our architecture, it would be something like this: header, rows, free space, and row offsets. Row offsets are in hex numbers and are showing starting positions of each row in the page. Now we understood the positions of the data in the page and how they are organized. Now let's try to read them by decoding them. Every row data in SQL Server consists of these parts: status A, status B, fixed data offset, fixed data itself, number of columns information, null bitmap, number of variable length columns information, offset for variable columns, and variable data itself. Here is the explanation, you can see. Let's try to decode the row based on this row structure. For this, first I copy the first row in our page. First 1 byte is status A tag, which is usually 30 in SQL Server. Let's color this accordingly. Next byte is status B, which is 0, indicating this is not a host record. Okay, I often see this is 0 usually. Next one is fixed data offset, which shows where the fixed data is ending. It is 2 bytes, okay? So one important point here, you should swap positions to find the value. What is hex of this C? It is 12, right, in decimal. This means that at 12th byte position, fixed data is ending. Let's now find where the fixed data. For this we count 12 bytes. This 4, 8, and 12 bytes, right? So this part is fixed data. Let's swap positions of bytes. First one equal to 1 in decimal. Second one is 101. Wow, bingo. Do you remember this? This is our first row, if you remember. We inserted, right? So we got the data. Next 2 bytes show number of columns in the row. We just swap positions of byte and find 3, which is correct, right? Because we were inserting 3 columns, right? If you remember. Then null bitmap, which is usually equal to 1 or 2 bytes, depending on the number of columns you have. Okay, here we have 1 byte. Then we have 2 bytes showing number of variable length columns, which is 1 here. This is exactly same as we have 1 variable column here. Then we have variable column offset, which shows the ending of variable column position. Number of variable column is 1. We multiply 1 by 2 and it becomes 2, right? So we take 2 bytes and find decimal, which is equal to 23. So our variable column is ending at 23rd byte. Let's count. Okay, until end we have 73 bytes, right? So this is variable column. If we change this hex to character by using ASCII, we find that this is Alex, which becomes our variable column value, right? So this becomes our row structure. So in this session, we understood the internals of data pages. We will focus on index pages in the next session. Thank you for watching.